Hello everyone, welcome back to Simon's Cybersecurity. Some of you who watched my earlier video on Citrix Bleed 1 last year, you have left some great comments to that video. There was good response. And now in the wake of Citrix Bleed 2 vulnerability, many of you in the comments are asking for a follow-up video explaining the Citrix Bleed 2 vulnerability. And that is why then here we are. This video is dedicated to understanding the latest Citrix Bleed 2. And so in this video, we will break it down together. We will really understand what makes this attack work, why it matters, how it differs from previous Citrix Bleed 1, and what lessons we can learn. So let's get started then. So up here on the slide, I am sharing with you what you will learn in this video. I have divided the video into 5 sections. In section 1, we will understand what are the use cases for Citrix NetScaler, why organizations use it, and then we will take an introduction of the Citrix Bleed 2 vulnerability. We will see how it differs from Citrix Bleed 1. After that, then in section 2, we will cover some programming basics such as variables, memory, and initialization concepts. These programming basics concepts are very essential. They are kind of prerequisites for you to understand what this vulnerability is about. So if you are from a non-coding or non-application security background, then this section will serve as a prerequisite, as a foundation for you to further understand the vulnerability. In section 3, we will simplify the vulnerability in a layman's perspective by using a everyday office meeting room analogy. After that, in section 4, we will cover some basics of HTTP post request because this attack is based on HTTP post, and how the attacker with minimal input can trigger this vulnerability and this attack. We will understand that. Just like programming basics was a prerequisite in understanding this vulnerability, in the same way, basics of HTTP are also required if you want to understand this vulnerability. Then in section 5, we will take a look at the root cause of this vulnerability and a conceptual difference between the vulnerable code and the fixed code. So I do not have access to the code of the security patch that was released by NetScaler. So I have used some ChatGPT and Google Gemini to understand what a conceptual fix would look like, what the conceptual the security patch code would look like to fix this vulnerability, and we will discuss on that and before closing this video. All right, then let's get started with section 1, in which we will take an introduction on the Citrix NetScaler. We will understand why it's important for the organizations, and we will then look at the introduction for Citrix Bleed 2. Now, for those unfamiliar with Citrix NetScaler, I have created this slide to give you a basic understanding of what Citrix NetScaler is, what services it provides, and why organizations use it. So Citrix NetScaler, it's a network device. It's an enterprise network device that provides services such as load balancing, firewalling, and most importantly, a secure remote access service like VPN to its users. Now, here's how it typically works. Remote employees, they connect to their organization's Citrix NetScaler gateway through a secure URL that is provided to them by the IT team. So they either open the URL in the browser or in some Citrix NetScaler agent that is installed on their endpoint. And after authentication, they gain access to a suite of applications, resources, and even full virtual desktops that are needed for their work. Now, you might wonder, why use Citrix NetScaler instead of a regular remote access VPN, right? The key difference lies in delivery. A VPN simply extends your office network to your device, but Citrix NetScaler delivers you a full virtual workspace. That means you are working inside a secure container inside an isolated virtual desktop environment that contains all your work tools, applications, and corporate data. And then this way, your organization can ensure performance and security at the same time. And let me illustrate this with an example from my own home. My wife, who is a doctor, she works for this healthcare company, and her healthcare company is governed by these various regulations like HIPAA and other compliances. And so her company has provided her with a very basic laptop, which has minimal specifications, which is very tightly controlled. There are no pre-installed apps on it, or even email access locally is restricted. And every day her work starts with her logging into the Citrix NetScaler portal using a secure URL. Once she's logged in, she's presented with a complete virtual desktop with all the apps, data, and tools that her team needs. And she can then work inside that isolated secure space. This way, the organization ensures performance plus security at the same time. And the security and efficiency, which means no sensitive data can be stored on her local laptop or copied out of this virtual environment. And performance is also optimized because everything runs inside that centralized virtual workspace, independent of her laptop's capabilities. So unlike a traditional VPN, which simply opens a tunnel into the office network, Citrix NetScaler gives users a fully managed, secure workspace for remote work. So I hope you have got the necessary understanding now of what Citrix NetScaler is, how important it is for the organizations. And with that context, then let's dive into the vulnerability Citrix Bleed 2, which is the core topic of this video. That's all on this slide. See you in the next one. All right, now that we understand what Citrix NetScaler is used for, let's look at what this vulnerability is about in brief. So this vulnerability was given the ID CVE 2025-5777 in the National Vulnerability Database of US, which is maintained by NIST. But in security world, this vulnerability is more of dubbed as Citrix Bleed 2. And at a high level, this vulnerability results in a sensitive memory exposure in NetScaler's authentication process, specifically in the authentication handler endpoint service. The key risk here is that sensitive information like credentials or session tokens can leak to unauthenticated attackers. And the attacker's action is simple. They don't need any authentication. They just have to send a malformed post request to the Citrix NetScaler box, and they can get the Citrix NetScaler box to bleed and reveal sensitive memory information. The root cause for this vulnerability is that the NetScaler ends up including uninitialized stack memory in its XML response, where a placeholder value labeled as initial value gets populated directly from the stack memory, and which may contain leftover sensitive data from previous logged in sessions. And this vulnerability was rated as 9.3 out of 10, which means it's very critical. Exploiting it is very simple. And what's more concerning is that it was already being exploited in the wild even before a public disclosure was made and even before a public proof of concept was released. So in short, Citrix Bleed 2 allows an unauthenticated attacker to send a specifically crafted post request and get sensitive data in return directly from memory without needing any credentials. And Citrix Bleed 2 is classified as a buffer overread type of vulnerability. A buffer, simply put, is a block of memory that a program temporarily allocates to hold data, for example, user inputs during a post request. And under normal circumstances, the system reads from the intended buffer exactly as needed. But in a buffer overread, something goes wrong. The system starts to read past the boundaries of the intended buffer into adjacent areas, which might contain leftover sensitive data from previous operations. This unintended reading of memory then can lead to serious information disclosure, as sensitive contents from neighboring buffers or memory locations can get exposed. And in Citrix Bleed 2 specifically, this overread occurs because uninitialized stack variables leak into the server's response. This is different from Citrix Bleed 1, where the core issue was a miscalculated response length leading to overreading. So in short, even though Citrix Bleed 1 and 2 differ in root cause, they both result in the same class of vulnerability, that is buffer overread and unintended memory exposure. So that's all on this slide. See you in the next one. Now that we have discussed what a buffer overread is, Let's take a moment to compare Citrix Bleed 2 with Citrix Bleed 1. So while both vulnerabilities end up leaking sensitive data from memory, their root cause, exploit path, and technical details are actually quite different. So I'm showing you the table on this slide. Let's walk through this together. Starting with the target, Citrix Bleed 1 mainly leaked session cookies. Session cookies are used by browsers to maintain your authenticated state. And in Citrix Bleed 2, it's the leakage of session tokens. They both serve the same purpose really, but just a different artifact that the attackers are trying to steal here. In both cases, what this means is that an attacker who gets hold of these cookies or tokens could hijack an active authenticated session and impersonate the victim user. Now, look at the root cause. Bleed 1 happened because of a misuse of the SNPrintf function's return value, which caused a miscalculated response length. Whereas Bleed 2 is different here. The problem is uninitialized stack memory being included in the server's response when a parameter is empty. Then the affected endpoints. Bleed 1 exploited OpenID related GET requests. Bleed 2 targets authentication.do, authentication handler service, via a POST request. The exploit methods also differ. Bleed 1 needed a malicious host header. Bleed 2 is even simpler. It just requires leaving a parameter empty in the POST request. And finally, look at the leak format. Bleed 1 leaked sensitive data in JSON responses, whereas Bleed 2 is leaking it in XML responses. So while they both share the same broad vulnerability class, that is buffer overread, the details and mechanisms are quite different. And understanding these differences is key because it helps us appreciate how similar risks can arise from completely different mistakes at the code level. So that marks the end of section 1. So in section 1, we understood what Citrix NetScaler is, what the device is used for. We took a brief introduction about Citrix Bleed 2 and how it is also classified just like Bleed 1 as a buffer overread vulnerability. And we looked at some key differences that are existing between Citrix Bleed 1 and Bleed 2. So this was a very brief introduction about the vulnerability. In next sections, we will dive deeper into the technical workings of this vulnerability. And in section 2, we are going to cover some programming basics like memory, variables, and initialization, and some more programming concepts which are essential before we do a technical deep dive into the working of this vulnerability. So that's all in this section. See you in the next one. All right, welcome to section 2. In this section, we will cover some fundamental programming concepts like how variables work, how memory is managed in C programming, and why initialization matters. Now, you might be wondering why talk about programming basics in a cybersecurity course, right? Well, to really understand the root cause of the Citrix Bleed 2 vulnerability, you need to grasp how memory and variables behave at a low level, especially in languages like C. Because the NetScaler packet processing engine of Citrix is written in C, C++. Now, don't worry if you're not from a coding background or you are new to application security. This section is designed to be simple, visual, and beginner friendly. So let's break it down step by step and build the foundation you need to understand this Citrix Bleed 2 vulnerability clearly. Let's get started then. Before we dive into the programming concepts, let me show you how all of this connects to the Citrix Bleed 2 vulnerability. It all starts with memory management. In languages like C and C++, memory management is not automatic. The programmer has to do it manually. Because of this, variables in C aren't automatically initialized like they are in safer high-level languages. And when a variable is left uninitialized, it might contain leftover memory content from previous operations. Now, if the program accidentally sends this uninitialized data back to the client, it can result in information disclosure vulnerability. And that's exactly what happened in this case of Citrix Bleed 2. A simple coding oversight led to a serious memory leak. So this slide is just to help you to visualize how these programming basics, memory, variables, and initialization that we are discussing are all chained together and how they ultimately lead to a vulnerability. All right, now let's start at the beginning by discussing the memory management on the next slide. All right, let's start our deep dive with memory management, one of the foundational concepts that directly impacts the vulnerability we are studying. In programming, when we create variables or objects, we need space in memory to store their data. Now, how that memory is managed, how it's allocated, how it's used and cleaned up can differ a lot depending on the language you use. In C and C++, which are low-level languages, memory management is manual. That means the programmer is responsible for allocating memory and also for cleaning it up when it's no longer needed. And if the developer forgets to initialize memory or clear it properly, the system won't help it. That's how uninitialized variables and memory leaks happen. On the other hand, higher level languages such as Python, Java, they handle memory automatically for you. When you create a variable in Python or Java, the language runtime ensures that the memory is initialized usually to null or zero so that you don't accidentally leak old data. What do you mean by null or zero or initializing the memory? Don't worry about these concepts. We will discuss them in detail on the next slides. For now, just understand that in higher level languages such as Python and Java, the memory management is automatic, it's initialized, and bugs like buffer overread and Citrix Bleed type vulnerabilities, they don't exist so often in Python and Java. But since the memory management is automatic in higher level languages like Python and Java, that makes the development easier and safer, but at the same time, there is a trade-off. These high level languages are also slow and less efficient when it comes to low level system operations. And that's where low level languages such as C and C++ still shine. Despite the risks, C and C++ are still widely used today in critical areas where speed, performance, and direct hardware access are non-negotiable, like in operating systems, network appliances, embedded devices, firmware, or even performance-intensive services like load balancers and traffic shapers. So, when you watch Netflix or when you're streaming something on Amazon Prime, the content delivery networks, their devices, when they are streaming the content to you, their code is going to run in C and C++ kind of low level languages because their speed and performance is very, very important. And in fact, products like Citrix NetScaler, where this vulnerability occurred, are also built using C or C++ for exactly the same reason, because you need to deliver speed and performance there. So you simply can't replace these languages in such use cases with higher level languages like Python or Java without sacrificing performance or control. So what we have learned on this slide is that while memory management in C, C++ introduces risks, it also gives what these languages require, that is power. And that's why understanding how memory works in C, C++ is crucial if we want to fully understand how vulnerabilities like Citrix Bleed to emerge. So with this understanding now, let's move on to the next key concept, that is variables and the two possible states a variable can have. So for now on this slide, if it was overwhelming for you, too much information, then just remember that in C, C++, memory management is manual, and that's why this causes some kind of problems, and this leads to the vulnerability that we are discussing. On the next slides, as you move ahead, you will form this comprehensive understanding of how all this fits. So just bear with me for a few more minutes and a couple of more slides, and this will all make sense to you. So now that we have looked at how memory is managed, let's talk about something that sits right on top of it: variables. In programming, A variable is simply a named container for storing data in memory. You can think of it like a labeled box where a program can temporarily store some information that it needs to work with later. For example, if you want to store a user's login ID, you create a variable called login ID. This variable will then hold whatever value the user provides, like Simon123 or admin123 or test user, whatever is the login ID of the user. And in the code on the right hand side here, I'm showing you the code of a program that is used for storing a user's login ID and how a variable can be used to hold that login information in the memory. So char login ID 256, char is the data type, login ID is the variable name, 256 bytes is the size of the memory that is reserved for this variable. So here we declared a variable named login ID that can hold up to 256 characters, but we are not leaving it empty. We are also initializing it. That means we are assigning it a starting value, in this case null, which is a placeholder that acts like a clean state. Why assign this null value? Why initialize the variable? Because the memory space assigned to that variable might still hold old junk data from previous tasks. So if we don't clean it first, unexpected values could be used or leaked later. So now when a real user logs in and enters his user ID like Simon123, that placeholder null gets safely overwritten with the new input that the user has provided. But here's something important. Not all variables are initialized. In some programs, a developer might declare a variable that is request memory for it, but forget to give it a starting value like null. And in that case, then that variable is called as uninitialized variable. So initialization means assigning a value right after the variable is declared. Uninitialization means no value is assigned. So whatever is already there in the memory space, that stays there. And that leads to unexpected bugs and security issues, because in that case the variable is in an uninitialized state and it might contain unpredictable data from previous memory use, and this can lead to unexpected behavior, and in some cases serious security vulnerabilities like Citrix Bleed can arise. So on the next slide, we will explore these two states of variable in more detail, that is uninitialized and initialized state in more detail, so you clearly understand the technical root of the Citrix Bleed 2 vulnerability. That's all on this slide. See you in the next one. Let's now talk about the two possible states in which a variable can exist: initialized and uninitialized. To make this easier to understand, I will give you a real-world analogy. Imagine you are checking into a hotel. Now, ideally, before you enter your room, the hotel staff cleans the room, removes anything the previous guests have left behind, they replace the bed sheets, reset everything to a neutral, safe, clean state, right? But imagine what if they didn't clean the room before handing it to you? You walk in and you find someone else's leftover luggage, food containers, or personal belongings. So the room now is messy, it's unpredictable, and even potentially dangerous for you. That's exactly what happens with uninitialized variables in programming. When a variable is initialized, it means the memory space reserved for that variable is cleaned up and assigned a placeholder value like 0 or null, something that marks it as ready to be safely used. So when valid user data comes in, like a login ID, it simply overwrites this placeholder value and everything works as expected. But when a variable is uninitialized, no value is assigned at all to it, then it means that whatever junk data existed in that memory location from earlier operations, it stays there. And if the program reads from that variable or sends it back as a response, that leftover memory, possibly some sensitive information, can be accidentally exposed. So in this slide, you see both cases visually. On the left hand side, you see initialized variable that is safely set to null, like a freshly cleaned room. And on the right hand side, you see the uninitialized variable example that still holds this 0xA3 value that is left over from a prior use. And that's how memory leaks and security vulnerabilities like Citrix Bleed 2 can happen. On the next slide, then, we will go deeper into this concept and show how uninitialized variables directly lead to leakage and how attackers can take advantage of it. Okay, so now that we have understood what uninitialized variables are, let's look at why they are dangerous, especially in the context of low-level languages like C and C++. So when a variable is declared and not initialized explicitly, the memory it occupies may contain some leftover data from previous operations. This is what we discussed on the previous slide. And this residual data, also known as garbage value, can accidentally get processed or even sent out in responses by the server to the client if the program code isn't careful about it. And in a security context, this is very critical because if the variable is part of a server's user authentication handling logic, then imagine the server might unknowingly leak old memory contents to the client. And depending on what's left in the memory, this could also include sensitive user data, session tokens, or other application level secrets. And this was exactly the problem in the Citrix Bleed vulnerability. An uninitialized variable, uninitialized buffer, when used in forming the server's response, it caused the server to leak out unintended memory contents to the client. Not because the server was hacked or the logic was bypassed, but simply because a variable in the code of its authentication handler endpoint wasn't initialized properly before use. And by initialization, as we saw on the previous slide, meaning it was not given a value, a placeholder value like null or zero. Just like we talked about this hotel analogy, like not cleaning the room before assigning it to the guest. So that's all on this slide. In the next slide, we will take our understanding of uninitialized variables a step further, because uninitialized variables are at the technical root of the Citrix Bleed vulnerability. So in next few slides, we will look at two specific scenarios that will illustrate to us how variable initialization or the lack of variable initialization can determine the outcome of a request. So that's all on this slide. See you in the next one. Now that we have seen how uninitialized variables can pose serious risks, let's explore this further through two practical scenarios. In both cases, let's assume that the variable on the server is uninitialized, meaning it might contain leftover data from memory. In scenario 1, we will see how the system behaves when a legitimate authorized user sends a properly formed request to the server. And in scenario 2, we will see what happens when an attacker sends a malformed request that is missing with expected inputs to a server that is having this uninitialized variable problem. So, what will be the outcome of the server? What will be the response of the server? We will see that, how it differs in both cases. So these two scenarios will help us clearly understand how the server behaves based on the presence or absence of the user input, and then why initialization is critical to prevent data leakage. All right, then let's explore these use cases in the next slide. All right, let's walk through scenario 1. Here we are looking at a typical case where a user sends a login request to the server, and the request includes the login ID parameter. For example, something like login ID equals to Simon123. Now, it's important to note that it doesn't really matter if this is a valid login ID or not. What matters is that the user has provided some value to this login ID parameter. The user has not left this login ID field empty. So, even if it's an invalid username or incorrect username or maybe some random string, string of letters, What is important is that some input is provided in the request by the user to the server. So in step 1, the user sends this input to the server. In step 2, the server receives this input and starts preparing the variable in memory. At this point, the memory location for login ID might still have leftover data from a previous request. This is the uninitialized state. Maybe it contains a random value like 0xA3 from previous operations. Since this is an uninitialized variable, it is not initialized, meaning there is no placeholder like null or 0 assigned to this variable. So whatever is there in the previous operation, that is, that those content are still lying in that memory region. So now comes the step 3. Since the user gave an input, the server can safely overwrite that memory location with the new value. And in this case, Simon123 was given by the user, so this is where things are safe. The old memory content gets written with the new value that was provided by the user. Now in step 4, the server uses that freshly written value to generate a response. It might prepare a session token or some login related output. If the login ID is right, then the server will give the actual valid token to the user for that author with that authorized session. If the login ID is incorrect, the server might give some kind of login related output, maybe some error or something else. But the important thing is that the input was provided by the user, some value was given to the server to work with, so the server was able to process this request normally. And then in step 5, the server sent the response back to the user. Since the memory was properly overwritten with the user input, there is no risk of exposing old or leftover content from the memory. So all is good, life's good here. The big takeaway here from this scenario 1 is that as long as the user sends some input, even if it's incorrect, the server has some input to work with. It will then override the memory with that new input and the situation remains safe. The problem doesn't arise from invalid input. It arises when there is no input provided at all in the login information. When login ID is left as blank and sent to the server. That is where then the server does not have some input to work with, and that is where the real problem starts because of this uninitialized variable that we will explore in scenario 2. Now let's look at scenario 2, which is where things get risky. This time the request is a bit different. The attacker sends a login request but leaves the login ID parameter completely blank. So it looks like this. Login ID equals to empty, missing parameter, no value at all. So in step 1, this empty request reaches the server. In step 2, the server receives the request but doesn't perform any check for the missing parameter. It goes ahead and starts processing the response. But here's the catch. Since there was no actual value provided for login ID, the server has nothing to override the memory with. Now look at this before state. The login ID variable has already been declared. Character login ID 256 carries the data type. Login ID is the variable name. 256 bytes is the size of this memory region that was allocated to this variable. That means the memory allocated for this variable, since it was not initialized, it holds whatever leftover data was sitting there before, maybe from a previous user session. So I'm showing it as 0xA3 here, just some random old byte. Then in step 3, because no input was provided, the memory remains unchanged. Nothing overwrites it. Then in step 4, the server sends a response, and this is where the problem happens. The response may now include this stale-over value from the memory, exposing session data, tokens, or other sensitive content from an earlier use. So the key difference here is simple. In scenario 1, the memory got cleaned and overwritten with user input in this step 3. But in scenario 2, in this step 3, since no input was provided, the memory stays dirty, left over, and that leftover content accidentally makes its way into the response that is sent back to the attacker. So this is the heart of the Citrix Bleed 2 vulnerability. The server didn't proactively initialize the variable, and it didn't validate that a required input was missing. That's why memory leakage occurred. So that's all on this slide. In the next slide, then we will talk about the mitigation for this and how it can help in these scenarios. Now that we have seen how missing input can lead to memory leakage, let's talk about how we can mitigate this risk. The answer is pretty simple: proactive initialization, but it's super effective. Here's what it means. The moment a variable is created, we assign it with a safe default value, like 0 or null or even an empty string. This happens after the memory is allocated. Now, in higher level languages like Java, Python, this is automatically taken care by the operating system during runtime. But in lower level languages like C and C++, you have to do it manually by writing a code for it. And why is that important? Because it ensures that the memory isn't holding on to any leftover junk from earlier operations. And how does this actually help? When the input is missing from the client side, like in our attacker scenario that we were seeing on the previous slide, then the system won't respond with stale memory. Instead, it will respond with the placeholder value like null or 0 or some empty string that was proactively assigned to this memory region when this variable was created, because you declared that in the code. And this completely then blocks the memory leak path that we saw earlier. And you can see in the graphic here that as soon as the variable login ID is declared, it's assigned with a safe default like 0 or null. That means when the response is prepared, no garbage data gets exposed, even if the user didn't send any input. So this is exactly what didn't happen in Citrix Bleed 2. And that's why this simple habit of proactive initialization can go a long way in securing your applications. Now let's take our understanding about this mitigation step a further by replaying the scenario 2 for the attacker request on the next slide. How proactively initializing variables can help prevent data leaks from memory. Now let's replay the scenario 2. Let's take a look at how this mitigation changes the outcome when the same attacker sends a blank login ID again. So we are replaying the scenario 2, but this time the outcome will be different because we have applied the mitigation of initializing the variable to a safe default value like 0 or null. So step 1, the attacker sends a post request to the login endpoint to the server, but leaves the login field empty, no input provided, just like before. And then the server receives this empty input just like before, but this time something important has changed under the hood. Here the variable is initialized with a safe default value, and that is the critical part. Step 3 is very critical here. Earlier, this is where the problem happened in scenario 2, where when no input was provided by the attacker, that meant no overwriting of the earlier memory. And then the server accidentally used leftover memory content in its response, and that could have leaked session tokens or other sensitive data. But now, since the variable is initialized with these values, even though no input has been received from the attacker side, the variable login ID will not have any problems because it was already initialized at the time of memory allocation. That means instead of containing garbage or leftover content, the memory reserved for the variable now is holding a clean, safe default such as null or 0. So even though the server has nothing to write here, at the same time, it also does not have to deal with old unsafe data anymore. It will simply proceed using the already initialized safe value in its response. And as a result, then the server sends out a clean response that contains only the safe default. No memory leak, no exposure, no risk. So even though the attacker sent the same blank input, this time the vulnerability is closed. And that's the power of proactive initialization. The safest value is already in place before anything ever gets processed. This is like that hotel room analogy where the room is already cleaned before the guest is assigned with the room. All right, then. I hope you have gotten a sense of what this vulnerability is about. In further sections, we will break down this vulnerability with more examples and more technical details. All right, then. Thank you. That's all on this slide. All right, that's the end of section 2. Let's wrap up section 2 with a quick summary of what we have learned so far. So we began our section 2 by chaining the root cause, showing how the Citrix Bleed 2 is rooted in basic programming concepts, memory management, variable usage, and initialization. And then we started our section 2 by learning about manual memory management in C and C++, how in higher level languages like Python and Java, memory management is automatic, but in C, C++, developers have to explicitly handle this. It's a manual process, or they have to face potential security issues. Then we took a look at variables. What are variables? We understood that variable is simply a named space in memory that is used to store some information, like a user's login ID. And then we discussed the concept of initialization, which means assigning a known value such as null or zero or a placeholder to that variable's memory. Then we talked about uninitialized variables, which occur when memory is allocated but no value is assigned. In such cases, then the memory may still hold leftover data from previous operations, and that might accidentally leak sensitive information to the attackers. And then we explored the dangers of uninitialization through two practical scenarios. In scenario 1, everything worked safely because the authorized user was providing a valid input, and more importantly, an input was provided. Whether it was valid or invalid doesn't matter, but if an input is provided, the old memory still gets overwritten, and it's a safe scenario. But we discussed scenario 2 as well, where we saw how sending a blank input could trigger a memory leak. And then we discussed the mitigation, that is proactive initialization of variables when they are created. And we replayed the scenario 2 to show how the outcome would be different if there is proactive initialization as a mitigation applied to this vulnerability. So that was section 2, where we used code and technical walkthroughs to understand how this vulnerability works at the programming level. Now in section 3, we will do a little transition. We will take a different route. We will simplify these same ideas using a real-world analogy of an office meeting room to help even non-technical folks understand what this vulnerability is about in a more relatable way. So in section 3, we will step away from code and technical explanations for a moment and then break down this vulnerability with a more intuitive and layman's perspective. All right, then, that's all in this section. I will see you in the next one. All right, so welcome to section 3. So far, we have looked at the Citrix Bleed 2 vulnerability from a technical lens, talking about how uninitialized variables and manual memory handling in C, C++ can lead to information leaks. Now, in this section, we are going to simplify the entire concept using a layman-friendly analogy. So we will use the idea of a meeting room to help visualize what variables in memory buffers, memory spaces really are, and how improper cleanup or lack of initialization can lead to unexpected data exposure. And toward the end of this section, we will also take a moment to reflect on something important. That is, why do developers sometimes skip initialization? Are they stupid, or is it some deliberate act? So this section will give you a clearer, more intuitive understanding of the vulnerability and also a balanced view of the real world decisions developers have to make while developing engines like NetScaler packet processing. All right, then let's dive into this section. All right, then let's break this concept of uninitialized stack memory down with a simple analogy, a meeting room in the office. So here I'm showing you the graphic of a meeting room in the office, and I'm also showing you what these different elements, what they represent. For example, what the meeting room represents, what this facility person standing here represents, wiping the whiteboard and all these different components that I'm showing you, what they symbolize. I've added the callouts here. So now imagine your company has a lot of meeting rooms, and when you book a meeting room, your company's facilities team, they get this room ready for you. They arrange the chairs, table, whiteboard, everything you need is allocated for your meeting. Think of this allocation like memory buffers or memory space that is being reserved in a program. Now, inside this meeting room, there is also this facility person assigned to you to help you during your meetings. And this facility person has two jobs, two simple jobs. First, they will wipe this whiteboard clean when needed. And second is they will write down any notes you give to them on this whiteboard. So, in a normal situation, this is what will happen. You will walk into the meeting room with a sheet of notes in your hand. You will pass it to this facility person. Since you have given them something to write, they first take a moment to wipe the whiteboard clean, whatever was there from the previous meeting. This is important that they wipe anything that might have been left over from the previous meeting on the whiteboard. Once the board is cleared, they will now carefully write your new notes on it. Clean slate, fresh content, everything works as expected, job done. So this is exactly what happens when a legitimate user sends something like login and their user ID or some input along with login ID to the Citrix server. The server, or in our analogy, this facility person, they see some kind of input and then immediately overwrite the previous memory with the new content that you have given or the user has given. It's safe because whatever was there in that buffer space from before, it gets replaced now with new content. So that's how the normal situation plays out, all safe there. Now let's discuss another possibility where things can go wrong. For that, imagine there is a rogue employee within the company. This employee realizes after a few experiments that this facility person only wipes the whiteboard when new notes are handed over. So if someone walks in empty-handed, this whiteboard is left untouched, still holding content, whatever was there written from the last meeting. So the rogue employee realizes this as a loophole and decides to exploit it for information disclosure. So they book the meeting room and they walk in empty-handed with no notes, nothing to write. The facility person welcomes them, but then notices that there are no notes being handed over. So they don't wipe the whiteboard clean. They don't write anything new because there was nothing given to write. And the rogue employee now has full visibility of the notes left behind from the last meeting's participants, which could include confidential project updates, executive decisions, or sensitive strategy documents. This is how information disclosure happens. And once the attacker understands this pattern, they start booking more meeting rooms across the company, exploiting the same flaw to extract information again and again. And this is how Citrix Bleed 2 worked. Whenever a legitimate user provided a login value, the server cleared and reused the memory buffer safely. Similarly to, say a good employee booking this meeting room, handing over notes to this facility person to write, then this facility person, since it sees there is something to write, they will wipe the whiteboard clean and overwrite it with new content. But when this rogue employee walks in, he walks in empty-handed, does not give any new notes to write, and thus this wiping off of the whiteboard does not happen, and there is information disclosure. Similar to when an attacker sent a request with an empty login parameter like login is equals to blank, the software of Citrix NetScaler didn't write anything and didn't bother clearing the memory beforehand. So whatever was left in that memory buffer from earlier sessions just got exposed in the response. And that's where the concept of initialization really matters. Initialization, from previous slides we understood, it means assigning a known clean value to the memory, like wiping the whiteboard clean before the next meeting starts. It makes sure that what you see is only what you intended to write and nothing left over is there. And uninitialized means nothing was done. The buffer, the space that was allocated, was never cleaned. The software didn't touch it. So whatever garbage or sensitive information was already there in that memory, it just stayed there. Similar to our meeting room scenario with this rogue employee. When the rogue employee booked the meeting room, handed nothing to write, then the meeting room was allotted with all the resources, including the whiteboard, to the rogue employee, but the contents from the whiteboard were not wiped clean because there was nothing given to write. Now, someone might highlight for right reasons that why does this process of meeting room has this flaw in it, where when the meeting room is allotted to someone, why the contents from the whiteboard are not cleaned before handing over the meeting room to someone, or why do these resources when they leave they not wipe the whiteboard clean. And similarly, in the Citrix Bleed 2 case, why didn't the Citrix NetScaler packet processing engine software not proactively wipe all the buffers, the allocated space, clean every time? We will explore those questions on the next slide in detail. That's all on this slide. See you in the next one. Now, let's take a moment to answer an important question that comes up when discussing bugs like Citrix Bleed 2. The question is, are developers stupid for leaving memory uninitialized? In my opinion, the answer is obviously not. It's rarely about developers being stupid and far more about the complex interplay of performance optimization, legacy design choices, and the inherent challenges of low-level programming. So, let's see the three main reasons here. The first one is performance optimization. So in systems handling immense network traffic like Citrix NetScaler, every CPU cycle and every memory operation counts, and initialization would cost you more CPU cycles and more CPU resources. Just like in our previous example, if we make the facility person wipe the whiteboard every time, regardless of whether the guest has anything to write, it would slow down the facility staff and waste their effort. Similarly, in programming, explicitly zeroing out or initializing every memory location upon allocation, especially for large buffers, large spaces, or frequently used variables, will introduce measurable overhead and slow down the system. Developers, particularly in low-level languages like C, C++, then they often choose to leave memory uninitialized, assuming that the next operation will immediately overwrite it with valid data. This is a calculated risk based on the expectation of normal execution flow. Imagine that if there is a variable which is going to be frequently overwritten very fast, then initializing it and then would cause you more CPU cycles. It would add time delay. And if you look at internet works on these network devices that are programmed on these low-level languages such as C, C++. Even your operating system is programmed on the low-level language. In that low-level language, the time domain is very different. Everything is happening at lightning speed. You pull up a web page, you post something, it's all very fast. The human time domain is very, very different and slow. When you wipe off something, it's slow, you can afford it, and you might think it's not a big deal. But when you travel into the time domain of these low-level languages, there the time is very fast. It's ephemeral. It's lot of information is getting exchanged. It's dynamic. There, if you even a micro nanosecond delay can add delay to the operation and decrease performance, because there these network devices are handling immense amount of network traffic per second. So there it's a trade-off between security and performance. This situation highlights, I agree, a classic trade-off, where a security conscious approach would have helped, but realize that initializing all memory, performing robust input validation, and handling all error conditions gracefully, that reduces the risk, but at the same time can impact performance tremendously. And there you have to keep some kind of balance, some kind of performance optimized approach. So, making assumptions about input, skipping redundant initialization steps, and prioritizing speed is normal. This can lead to impressive performance. And additionally, this is an example of an edge case. Security vulnerabilities like Citrix Bleed 2, they often arise from unexpected or edge cases that are not considered during the initial design and optimization phases. So we can clearly say that the problem isn't that the developers are stupid, but the problem is that it's nearly impossible for them to anticipate every conceivable malicious input and how it might interact with optimized code paths. So that's all on this slide. I will see you in the next one then. This is the end of this section. And in the next slide, we will summarize what we have discussed so far on this section. All right, that brings us to the end of this section. So in this section, we took a step back from technical details and used a real-world analogy to simplify the concept of uninitialized memory and how it leads to Citrix Bleed 2 vulnerability. And after that, then we also discussed from developers' perspective, like what developers are thinking when they are coding in the low-level languages and the network devices that work on these low-level languages. For them, you have to keep this performance optimization approach in mind, because security operates on this principle of reducing functionality and decreasing performance. So it's always a trade-off between performance and security. All right, so we will move on to section 4 now, where we will cover some basics of HTTP post request, which are very essential to understand the Citrix Bleed vulnerability. So I will just, like how I gave you the basic understanding of programming concepts in section 2, in this section 4, in the first slide, I will give you a basic understanding of what HTTP post request is and what it means when such a request is malformed. All right then, see you in the next section. Welcome to section 4, where we will break down the basics of HTTP post request and then also look at how a basic HTTP post request is different from a malformed HTTP post request. And we will also look at a screenshot of Postman that I'm showing you from my machine. I have posted some visual callouts on the screenshot to show you that how trivial it is to exploit this vulnerability, how with minimal effort and a simple tool like Postman, the attackers can exploit this vulnerability. All right, in this section, we are going to dive into the technical details of the Citrix Bleed 2 attack. But before we do that, it's important that we talk about the HTTP post request. We understand what HTTP post request is. So, just like we explored programming fundamentals in the earlier sections, like memory variables and initialization, to make sense of how the vulnerability works, similarly, we also need to understand the basics of HTTP, especially the post method. And that's because this Citrix Bleed 2 vulnerability, it's centered around a malformed HTTP post request attack that the attacker would carry out. So to truly grasp what's happening, we first need to get comfortable with how a typical standard non-malicious post request looks like, how it works, and then we will be able to make sense of how a malformed HTTP post request would look like and behave. So let's break that down then. Let's get an overview of HTTP post request. So HTTP basically is the protocol used by web browsers and servers to communicate with each other. So when your web browser from your laptop is communicating with google.com or Amazon, then it's doing that using the HTTP protocol. It is short for Hypertext Transfer Protocol. And there are different types of methods that are available in HTTP to interact with the server. So the client-server interaction that takes place via different methods. Some of the most common ones are HTTP GET method, HTTP POST method, HTTP PUT, HTTP DELETE, HTTP UPDATE. PUT, DELETE, and UPDATE are mostly used by administrators. HTTP GET and POST are the most common ones that are usually used by the common folks like you and me. So HTTP GET is used to retrieve data. For example, when you open a web page like google.com on your laptop, then your browser will send a GET request to the Google server asking for its page. Similarly, HTTP post would be when you want to send some data to the server. Think of actions like submitting a form, logging in, uploading a file, or interacting with an API. So in all these use cases, your data is bundled inside the body of the request and sent to the server. So when you type in instagram.com, you use the HTTP GET method to get the initial page of the Instagram. And when you're logging in to your Instagram, then when you type in username and password, then you're using the HTTP post method to post that information to the Instagram server. So logging into the server, posting your authentication information to the server, that's to the HTTP post. And that is quite different from a GET request, because in the GET request, the data is appended in the URL. But in the HTTP post, it keeps it in the body, making it then more suitable for things like form submissions or authentication requests. Now, there is also something called encoding type. In a typical post request, you will see something called a content type header, which tells the server how to interpret the incoming data that you are sending with your browser. And a common format is application/x www form URL encoded. In this format, data is sent in the form of key value pairs. So key would be like, if I have to take an example of login ID information, then login ID would be your key, and your username would be the value that you will be sending. So login is equals to test user, login becomes the key, test user becomes the value. And so in the form of this value and pair, you are sending this data to the server. And it's very important. I mean, if you don't send value, or if you just send value and not key, then if you don't send it in this pair format, then it becomes a malformed HTTP request. We will look at that on the next slide in detail. And then there is also this multi-part form data, which is not very important from this Citrix Bleed perspective. From Citrix Bleed 2 perspective, only this application X form URL encoded is important, because this ties to the vulnerability that we are discussing. Multi-form part data, this is mostly used for uploading files or images, and which might be used in other forms of attack, but not in the Citrix Bleed one. So we can say that HTTP post is the method by which you are sending your logging information to the server, and then server is in its response giving you your login token, your session token or session key. So that is all in this slide. Then I wanted to give you a general overview of what HTTP post request looks like, what it is, so that on the next slide, when we are discussing the malformed HTTP post request, the malicious HTTP post request, you will understand what that is. All right, then that's all in this slide. See you in the next one. All right, now that we have understood what a normal HTTP post request looks like and what it's used for, let's take a look at the malformed post request. So a malformed post request refers to an HTTP post request that the server cannot process because of an error in its syntax or structure. So if a client sends a HTTP post request to the server, and if there are some values missing in it, then the structure is broken, the syntax is incorrect, and the server will not be able to process it, and the server will give an error in its response to the client. And as we saw on the previous slide, that when you are sending login information to the server, the encoding type typically used by a browser for that content is application/x www-form-URL encoded. In this format, the server expects the data to come in key value pairs. It looks for both a key and a value corresponding to it. But in the case of a malformed post request, like the one I'm showing you here, only the key is being sent. So this is the snapshot of the malformed post request that is usually used in the Citrix Bleed 2 attack. And if you see here, there is no value provided. So instead of the usual key plus value, that is login is the key, and the ID, whatever the login ID or the username, that is the value, that is not provided. It's just the key that is provided by the attacker. Just this login label name, the key. And this breaks the expected structure for the server, because since a typical authentication relies on this complete key and value structure, omitting the value makes the request faulty. The server then can't process it properly because there's a syntax error in the body of the request. And in a normal non-vulnerable server, this kind of request would usually be rejected, and you would get a 400 bad request error, and there will be nothing else leaked from the memory. But in a vulnerable server, one affected by something like the Citrix Bleed vulnerability, there this malformed input leads to unexpected behavior, meaning instead of cleanly rejecting the request, the server might go ahead and respond. And in doing so, it could leak chunks of uninitialized memory. That leaked memory may contain sensitive information left behind from earlier operations, like session tokens or login details for previous users. And that's really what makes this so dangerous. The attacker isn't doing anything complicated, they are just sending an incomplete post request. But because the server doesn't handle it safely, it ends up bleeding private memory content in the response. And as I mentioned on the last slide, different types of data use different encoding formats. If you are uploading files or images, the browser uses this multipart /form data. For login information, it uses this application X form URL encoded, which expects a proper key value formatting. And when that format is broken, like in this malformed post request, the server struggles to handle the request. And if the underlying implementation isn't secure, meaning if the memory allocation is not properly initialized, if the buffers are not properly initialized, then things can go really wrong. And yeah, so now let's move ahead to the next slide, where I will show you how attackers can craft such a malformed post request using a simple tool like Postman, and then how that can make the server bleed sensitive data. All right, let's take a look at this screenshot from Postman, where I'm demonstrating just how simple it is to trigger the Citrix Bleed 2 vulnerability using minimal tooling and minimal input. First, to be clear, this is for educational and awareness purposes only. My goal here is not to encourage any kind of attack or misuse of tools like Postman. I'm simply walking you through how this malformed post request looks like in this Citrix Bleed 2 attack. So let's get started then. So here in Postman, you can see that I have selected this HTTP post method. That's done using this drop-down menu on the top left. And the target URL that is given here, it is pointing to this authentication handler endpoint of Citrix NetScaler, that is /p/u/do authentication.do. This is the authentication handler in the NetScaler packet processing engine, which is the actual code responsible for handling the authentication from the users. And this is the same endpoint that is getting exploited in this vulnerability. Next, notice the headers and the body setup. The headers are standard, nothing special or privileged required here. There is no authentication token being passed, no API key, nothing. That means that an attacker doesn't need to be logged in to trigger this flaw. It can be done anonymously, unauthenticated way. And in the body of the request here, if you see, there is a malformed input. In this case, it's just a single key named login with no value assigned to it. And normally you would expect something like login is equals to test user, or login is equals to some username. But here it's just login and nothing else. The value is empty. And that's the malformed post request we talked about earlier, missing the equal to and the actual value. And that's it then. This tiny input, when sent to vulnerable server, it is enough to cause the system to leak sensitive memory in the response. And that memory might include session tokens or other private data from past users. So that's all then. With this slide, I just wanted to illustrate that how trivial it is to exploit this vulnerability. And yeah, to emphasize again, this is not a hacking tutorial. And yeah. That's all on this slide. See you in the next one, where we will do a technical walkthrough. I will show you a diagram of what are the steps involved in triggering this memory leak. All right, Now that we have seen how the malformed post request is crafted, let's walk through what actually happens inside the Citrix NetScaler device when the request is received. So on the slide here, I'm showing you the walkthrough that I've broken down into 5 key steps. Starting with step 1, I'm showing you the attacker sending a crafted HTTP post request to this authentication.do handler endpoint. This is the authentication handler we looked at in the Postman example. And this malformed post triggers a flawed handler then. And since the server receives this request, because the input is incomplete, it's missing this value part, it doesn't follow the expected format, the syntax is broken, the structure is broken, and that's where the things start to break down inside the Citrix NetScaler. Then step 3 here, I'm showing you the NetScaler authentication handler that is receiving this broken request, and instead of rejecting it with a clean error message, which would be a secure behavior, the handler tries to proceed with this request anyway, which brings us to the step 4. And here's the core of this vulnerability. Since the input is missing, the server doesn't have a valid value to work with, but it still allocates buffer space in memory for that expected input. So a buffer space is still allocated for this login ID input that is provided. And that buffer space never gets initialized, meaning whatever data was already sitting there remains untouched. So whatever data was left over from previous operations, that remains untouched, it's not overwritten. And then the server in its response, it starts to prepare this response, and it takes this leftover memory, wraps it in an XML file in a tag called initial value, thinking it's valid data. And then step 5, the server sends this XML response back to the attacker, and that's where the leak happens. And that initial tag contains sensitive memory content from operations or users, session tokens, authentication details, or whatever was left behind in that memory space by previous operations. And the presence of this initial value tag in the response itself, indicates is an indicator of compromise. Indicates that the Citrix NetScaler ADC and gateway devices are vulnerable to this bleed vulnerability. This tag is not a standard or intended part of a normal authentication process, and it should not be present in the response that a user receives. And its presence then indicates that the system is revealing sensitive memory content due to this vulnerability. So this is how a tiny malformed request with no credentials or special access can lead to a serious data leak, all because of uninitialized memory being included in the response. So in short, malformed input in, unhandled memory out. And that's how you can conclude this. So that's all then on this slide, and the previous section 2 where we discussed this in detail. I hope that is all making sense to you now, and that is forming a complete picture in your mind, a comprehensive understanding of this vulnerability now. All right, with that we end our section 4. In section 4 we started it with looking at what a HTTP post request method means, how does the normal standard HTTP post request looks like, how a malformed HTTP post request looks like for the Citrix Bleed attack, and then I showed you a screenshot of Postman to show you how trivial it is to exploit this vulnerability. And then finally we broke down the steps of attack through a theoretical technical walkthrough on the slide. And now we will proceed to section 5 then, in which we will look at the vulnerable pattern in the code and a conceptual fix pattern. All right, see you in the section 5. All right, welcome to section 5. In this part, we are going to look at the vulnerable code pattern behind Citrix Bleed 2 and how a conceptual fix in the form of a secure patch, what the code of that secure patch would look like. Now, to be clear, that these are not the actual vendor patches that I'm going to discuss with you. These are just conceptual examples that I have drawn using AI tools such as Google Gemini and ChatGPT. They are meant for pure educational purposes. I'm not discussing any official patches, secure patch code with you. In my previous course, previous video on Citrix Bleed 1 that I did 1 year ago on my channel, I was able to include the actual reverse engineered patches and show you the code. They were reverse engineered and published by, I think, a company called Asset Note. But this vulnerability, Citrix Bleed 2, is still very recent. As of now, no one has publicly reverse engineered the Citrix's patch for this one, especially the secured patch. No one has reverse engineered it, and doing that at home for me would require tools like Ghidra and some more open source software engineering tools, and a lot of time and a dedicated lab, which I don't currently have. So instead, what I've done is I have recreated the vulnerable pattern and possible secure coding approaches that could mitigate such issues in general, and we will do a general discussion on that in this section 5. With that said, let's move into the section 5 then. All right, now let's look at how this vulnerability plays out in the NetScaler handler's code logic, conceptually, of course. So the root cause in Citrix Bleed 2, as we have understood, it's pretty straightforward. The memory for a variable, in this case, login buffer, is allocated on the stack, but is not initialized. And then if the attacker sends a post request without any value for that login buffer, for that login field, then the buffer remains uninitialized, and in the response, the server starts leaking sensitive memory information. So on the right side here, I have included a conceptual code snippet to help you visualize how this flaw might look like. Again, this isn't the actual source code from Citrix. It's just a simplified example based on public information and analysis. So as you can see, there's a function called handle_login_request, which extracts the login field from the request body. And if the login field is missing, if the login field does not have any value, then this buffer username_buffer, this is never assigned with anything. This remains uninitialized. And later, when the response is assembled, it still includes the contents of that buffer using the initial XML tag, initial value XML tag. So then the presence of this initial value XML tag in the response itself is an indication that your server is leaking some kind of memory information. So in short, the buffer is declared, this variable is declared, but it is not initialized. That's why you don't see anything equal to and some value like null or 0, which are the starting value that can show that the variable, this buffer, is initialized. And obviously then when the attacker sends malformed input, the server tries to build a response based on this uninitialized variable, and there is unintended memory exposure then. So that's all on this slide. We will look at what a conceptual fix might look like on the next slide, and how this same logic can be made safe by handling the buffer properly. This slide, we are talking about two main approaches one can take to fix this vulnerability. Approach one is that right after allocating the buffer, we initialize it. That is what we call setting it to a safe default state. For example, you could just fill the buffer with null bytes or an empty string. That way, even when no valid input is provided, the memory won't contain any leftover or sensitive data. And then approach two is we tighten our response logic as well. So when we are preparing the HTTP response, we make sure that no part of the buffer is used unless we actually have written something meaningful into it. This adds an extra safeguard because it ensures that only valid data makes it to the response. So on the right hand side of the slide, I've shown an updated conceptual code snippet based on these principles. Again, this is not the actual vendor patch. This is just a generic example that I'm showing you based on the public research, and I've used Google Gemini to generate this possible secure patch code. So here, after declaring the buffer, we are assigning it a safe default, and before copying anything into the response, we have added checks to ensure that the data is valid. So even if the input is empty, when the attacker sends an input which is empty, the code either fills the buffer with an empty string or handles it gracefully. This is a simple but effective fix, and it shows how paying attention to edge cases like empty input can make a big difference in secure coding. And here you can see as soon as this variable username underscore buffer is created inside this handle underscore login request function, it is initialized with a null character and empty string, and we have added then these further if and else conditions to make sure that our HTTP responses are also checked before a response can be sent out. So that's all then in this section. I hope this has given you a comprehensive understanding of what Citrix Bleed to vulnerability is about. So in this section, we then looked at this conceptual fix and vulnerable code pattern, code logic, and that's all then. We will end this section by doing some final takeaways, like we have discovered in this video that Citrix NetScaler is vulnerable to this memory bleed vulnerability, and how it is, what is the root cause, like uninitialized stack memory is the root cause of it, which can lead to sensitive information leaks, and then variables and memory buffers, how they need to be properly initialized. But it's a developer trade-off. I mean, these are network traffic handling devices, so the more secure coding, the more security that you add to them, you're going to decrease performance and reduce functionality. And yeah, so that's how it works. So all right then, I hope this video has helped you in understanding the root cause of Citrix Bleed to vulnerability. If you have liked this, then do share it with your contacts. Thank you. I will see you in the next one.